In this video, we're going to talk about conditional probability. So conditional probability is the probability of one event occurring once you know that another event has occurred. That's where the given comes in. So you're restricting yourself, you're really restricting your sample space to a smaller sample space where one event has already occurred, and then figuring out the probability of the other event from there. We denote the conditional probability of B given A, given that A has already occurred, as B with that up and down line, A. It's called the probability of B given A. And it really is the proportion of all occurrences of A, of all those places where A happens, that's that restriction of the sample space, for which B also occurs. So when the probability of A is greater than 0, and we put that restriction on because if the probability of A were 0, then we would be dividing by 0 and we would have an undefined probability, which makes sense because if A can't happen, then how can you talk about what's the probability of B happening given that A has already happened if it can't happen? So that's why we put that caveat there. In all the instances, we will look at the probability of A is greater than 0, so we don't have to worry about it. So the math notation of this is the probability of B given A equals the probability of A and B divided by the probability of A. That division by the probability of A is again restricting that sample space to the places where only A occurs, and then that numerator is saying all the times that B also occurs within that. So for any two events, the general multiplication rule says that we can multiply the probabilities of one event with the conditional probability of the remaining event, given that the first one happened. So now we're taking that multiplication rule and we're taking out that need for independence, and we're saying we have a general multiplication rule we can use anytime if we introduce conditional probability into it. So the probability of A and B, you can figure it by either the probability of A times the probability of B given A, or you could call it the probability of B times the probability of A given B. And I think it would be a good thing right now if you stopped the video and actually wrote out that mathematical notation for the probability of B given A being the probability of A and B divided by the probability of A. And you can see on your paper when you do that, when you multiply by the probability of A, those cancel out, and what you're left with is the probability of A and B. So the notation is all hanging together too, and this is just different ways that we can look at it based on what we're trying to figure out and what we already know. So let's look at this case study real quick. At a certain university, 20% of freshmen smoke, and 25% of all students are freshmen. So let's let A be the event that a student is a freshman, and B be the event that the student smokes. What we know is that the probability of A, the probability that the student is a freshman, is 0.25, because 25% of them are freshmen. And we happen to know the conditional probability of B given A. In other words, we know what is the probability of that they smoke given that they are a freshman, because we're told that 20% of freshmen smoke. And what that means is we've limited our pool to just freshmen and found out that 20% of them smoke, so the probability is 0.20. So again, pause the video and take a minute to figure out what the probability is that a student smokes and is a freshman. So now that you're back, let's compare your answer with mine. Remember that the probability of A and B by the general multiplication rule is the probability of A times the probability of B given A. So you're going to multiply the 0.25 times the 0.2, and you should have gotten 0.05. In other words, another way to look at that is that we're saying that of the entire student body, 5% of them are freshmen who smoke. And there's the math of what we just did. So take a minute to look at that, pause if you need to, compare to what you've done, and make sure that your thinking is lining up with what we've learned so far. And then we'll move on. So independent events. We have already defined independent events as events that don't really depend on each other, like the knowing about one doesn't influence whether the other happens. But now we have this way to formalize that and say that if they have positive probabilities, in other words, neither of them has a probability of 0. They're independent if their conditional probability is the same as the regular probability. So the conditional probability of B given A is equal to the probability of B. In other words, that restriction of the sample space did not affect our probability of B happening. And if you look here at the general multiplication rule that we've just learned, and the multiplication rule that we talked about for independent events in the previous module, you'll see that the only difference is the probability of B given A and the probability of B. So that's how we get this notion that events are independent if the conditional probability of B given A is the same as the probability of B. Tree diagrams, extremely helpful tool. I'd say as helpful as the Venn diagrams that we talked about before. So let's just walk through one tree diagram and how they're done. They're useful for solving probability problems that have several stages to them, especially. And they combine a lot of the basic probability rules to solve a really complex problem that it's hard to get your head around. And that's the same thing that Venn diagrams do. When it's hard to get your head around what's going on, try a tree diagram for it. And we're going to have these branches of the tree. And we're going to multiply the probabilities on the segments to get to the end. And you'll see how this looks. But that's the basic notion of a tree diagram. We have the probability for each of the segments we can figure out. And then we just use the multiplication rule to get us to the end and to figure out our probabilities of reaching the end of any branch. Again, that doesn't make sense until you've seen one, so let's move on and look at one. Then the probability of an event is found by adding the probabilities of all the branches that are part of that event. So again, Not making sense till we see it. But you might want to come back to this slide once we've seen one and see how that works out. So we're going to have this binge drinking and accidents case study. So we have this college where 30% of the students engage in binge drinking. And among college-age binge drinkers, 18% have been involved in an alcohol-related automobile accident. Only 9% of non-binge drinkers of the same age have been involved in such accidents. So we're going to let A be an accident related to alcohol. A is that the person has been involved in an alcohol-related automobile accident. And event B is that somebody's a binge drinker. And if you look through the probabilities that we've been given the probability of A given B. We've been given the probability of A given not B. And we have been given the probability of B. We want to know what's the probability that we just randomly select some student at this college and we find out that they have been involved in an alcohol-related automobile accident. So we're going to set up a tree diagram to do that, and it's going to look like this. Okay, ignore this stuff over at the side for now. That's an explanation for how we get there, but we have to do this first, okay? So we have binge drinkers and non-binge drinkers. 30% of the campus is binge drinkers. That's where this 0.30 up here comes from, which leaves 70%, 0.70, to be non-binge drinkers. That's the first segment of our branches. From there, we know that 18% of those binge drinkers have been in an accident, which leaves 82% of those binge drinkers to not be in an accident. And of the non-binge drinkers, we know that 9% have been in an accident, which leaves 91% that haven't been in an accident. So that's the second segment of our branches. So let me show you. The branches are there, and then there, and then there, and then there. So one branch is binge drinkers in an accident. Binge drinkers in no accident is the second branch. The third branch is non-binge drinkers in an accident. And the fourth branch is non-binge drinkers from no accident. 2 segments on each branch. And then what we're going to do is this over here. We're going to multiply across our segments. So we're going to multiply 0.30 times 0.18 and get 0.054. We're going to keep doing this all the way down, and we're going to get each of these probabilities. So we know now what's the probability that a binge drinker, that a randomly selected student is a binge drinker that's been in an accident. It's 0.054. And on down the line. But what we wanted to know is we wanted to know this. What's the probability that they've been in an accident? We don't care for the question we're asking, whether they're a binge drinker or a non-binge drinker. We just want to know what's the probability that we randomly take a student and they fall in one of these accident categories. So to do that, now we use the addition rule. And we can add up the binge drinkers that have been in an accident and the non-binge drinkers that have been in an accident. And when we add those up, we get a probability of 0.117.